So folks, back to the Dickey-Fuller test. Will you pay attention to this? After 15 minutes, 10-15 minutes, this will switch off, so you need to switch that red button on. So the Dickey-Fuller test. What do you use the Dickey-Fuller test for? What do you use the Dickey-Fuller test for? To test whether a given time series is a random walk or not. Right? So you really have a model. Your basic model that you do. Suppose you have a AR1 process. Suppose we have an AR1 process where yt is equal to when will this process be a random walk? When phi is equal to 1. When will this process be stationary? When the absolute value of phi is less than 1. Right? So what we want to do is to test whether this time series is a stationary time series, which is really tantamount to testing whether phi equals 1. Okay? Right? What will the standard approach be? The standard approach will be regress y on yt minus 1. Right? Okay? You will get the estimate. What will be the estimate of phi hat? Summation yt minus 1 upon yt minus 1 square. That will be the estimate of phi hat. Right? What would be sigma hat square phi hat? Sigma hat square phi hat would be sigma square e upon summation yt minus 1 square. Why would sigma square phi hat be sigma square e upon summation yt minus 1 square? Because what is the formula for the variance of beta hat? Sigma square upon summation x hat. What is x here? Yt minus 1 square. Right? If you want to test the null h naught phi is equal to 1 against the alternative phi is less than 1 in absolute value, against the alternative phi, absolute value of phi is less than 1. Okay? Then what do you have to do? The standard approach would be you calculate the T phi statistic, right, which is phi hat minus 1 upon sigma hat square phi hat, right? That will be the T statistic, and then you compare it to the T distribution, right? If the statistic lies in the rejection region, you will reject the null hypothesis. Otherwise, fail to reject the null hypothesis. That is how usually, insofar as you have whatever you have learned in the first and second modules in this course, you do. But in this particular case for a time series, we learned that when phi is equal to 1 in absolute value, you cannot use the T distribution to test the null, because if phi is equal to 1, the process becomes a random walk, and for a random walk, you cannot do test of hypothesis in the usual fashion. So if your null hypothesis is actually phi is equal to 1, your basic presumption is that the data are a random walk, and therefore the usual test of hypothesis do not apply. So then you cannot go around and test that hypothesis itself, that the usual hypothesis tests do not apply, by using the usual hypothesis test. You cannot do that, right? So you need a different way of testing. Okay? So what you do, that was the test. The procedure was proposed by Dickey and Fuller. sometimes at the end of the 70s and the early 80s, right? The process goes like this. Okay? What Dickey and Fuller suggested was, think of yt minus 1 is equal to delta y, which can be written as everybody sees why this can be written like this. 5 minus 1 yt minus 1, we have separated yt minus 1 for both sides. Right? So 5 minus 1 will come out common, yt minus 1 will come out common, and what I'll have is 5 minus 1. What I'll have is 5. So, call this quantity gamma. Okay? And you have gamma. So the dependent variable is change in yt. The independent variable is yt minus 1. I am assuming that there is no intercept in the regression model for simplicity, but there can. There can also be a linear trend in the regression model, but we are keeping the things at the simplest possible level so that we can understand how things work. Right. Now, the null hypothesis phi equals to 1 implies gamma equals 0, because gamma is equal to 5 minus 1. Right? Sure? So what we are going to do is going to test the null. We are going to test the null that gamma equals 0 against the alternative that gamma is less than 0. Right? So it becomes a one-tailed test. In the Dickey-Fuller test, what we are doing is we are testing the null phi, okay, gamma is equal to 0 against the alternative of a one-tailed test where gamma is less than 0. That is, absolute value of phi is less than 1. Right? Okay? So if phi is 0.7, for example, then this will be minus 0.3. Right? So that's the kind of a problem that we are looking at. Sure? Okay? Right. So what do you do? How do you test this? Now the problem again is you cannot use the t-test. Okay? You cannot really use the t-test to do this. Normally in a regression coefficient, if you want to test whether regression coefficient beta hat is equal to 0, you take beta hat upon sigma hat beta hat, you get the t-statistic and compare. But here, because we have a non-stationary process, we have said that you cannot use that kind of a method of testing. So what you do? You therefore use a method proposed by Dickey and Fuller, which is based on simulation. You see, the problem is if you calculate the t-statistic, this will be the t-statistic, right? Gamma hat upon sigma hat, gamma hat, right? Which I'll call t gamma. The problem is I do not have a distribution to compare it with. Okay, the big problem is I don't have a distribution to compare this with in order to reject or fail to reject the null hypothesis. So what do you do in this case? You use a very computationally intensive method. Use a highly computationally intensive method. Suppose you have got a sample size of 50. Suppose this regression involves 50 observations. So what the computer will do is, it will generate a random walk on its own having 50 observations. So it will generate a random walk where yt is equal to yt minus 1 plus et. So we take some initial value of y, create y1 by adding to this y a random error term, then create y2 by adding to y1 a random error term, normally distributed with mean 0 variance 1, create y3, create y4, create y5, then create y5. Right, with the data are random. Then it will create delta yt, it will create yt minus 1, and do a regression from that data set. Calculate gamma hat upon sigma hat gamma hat. Calculate that t statistic. Store. Then generate a fresh random walk which is unrelated to the first random walk. Generate a fresh random walk. And again do the whole thing and again calculate a t statistic for this fresh random walk. Then create another random walk. Right? Create thousands of random walks like this. Right? So, and then create thousands of t statistics. Now, if you plot the probability distribution of this t statistics, what you have? You have the probability distribution, you have the probability density of the t statistic under the null hypothesis. So, this is how the t statistic is distributed when the null hypothesis is indeed true. Right? So, suppose that distribution looks like this. Suppose that distribution looks like this. Then what they will do is, because you have a one-tailed test, suppose this, say area to the left of minus 3.4 for example, contains 5% of this distribution. What does it mean? Given that the null hypothesis is true, probability, given that the data are a random walk, the probability that the t statistic which is calculated like this takes a value less than or equal to minus 3.4 is just 5%. Right? So what you now have? You have critical values with which you can compare your data set because you have the same number of observations and so on. Now, the computer will calculate this for your data. Suppose your data is some GDP series. Then it will create delta GDP, regress delta GDP on GDP minus 1, calculate a gamma, calculate gamma hat, sigma hat, and see whether your gamma lies here or here. Your T gamma hat lies here or here. If your T gamma hat lies here, it will say that look here, if the null hypothesis is true, there is a less than 5% chance of getting the T statistic so low, therefore we can reject the null at 5% level of significance. Otherwise, it will fail to reject the null. Is this clear? The important point here is that because there is no standard distribution to which we can compare our t statistic, we have to generate the distribution of the t statistic by simulation, right? Okay, every time that we want to take this test. Every time that we want to take this test. Sure? So if you have 50 observations, so three things are careful. This distribution is simulated. So it will depend upon three things. Two things here. It will depend upon the number of observations you have. Secondly,